Alright, ladies and gentlemen, welcome back. So, we're discussing how changes on Earth's surface are going to drive the evolution of organisms. And one of the things that we can't not discuss is this idea of plate tectonics, because this really is going to shape where we see the diversity of life exist, as well as just the distribution of organisms on Earth. And this is an interesting one because this is sort of geology supporting biology and vice versa. So let's go back to what plate tectonics is for a second. So when we look at Earth's surface, right, and we sort of drill into what that means, you've got your hard outer crust, and then you've got this liquid mantle underneath. And so really, the major continents are sitting on these plates, and these plates are floating just above on the surface of that mantle. And as a result of that mantle being fluid, that means that these plates are capable of moving. Interesting thing is that they do move in very predictable patterns. So when we look at where those plates exist and where they have existed in the past, we can see how those plates either are moving away from each other or moving towards each other, and that very much shapes the geologic features on those continents. So mountains where we see deep sea trenches and so on and so forth. And at those tectonic boundaries, we get a lot of geologic activity from volcanoes to earthquakes, so on and so forth. So again, most of the geologic processes occur at those plate boundaries. They're weak points in the plates themselves. So something like the fault along the edge of California, those plates, rather than smashing into each other or moving apart, actually slip past each other. They rub against each other, and so they'll rub and get stuck and keep trying to move, and eventually they'll let loose, and that's where we get a lot of the earthquakes from. Other plates will smash into each other and cause mountains to form. Others will separate, and you'll get these oceanic ridges and trenches. Others will slip underneath each other, which is where you get things like these subduction zones, and the forcing of that material back down into the mantle causes them to melt and can build up pressure for volcanic activity. So much of the features we see on land are as a result of plate tectonics itself. So where does this tie back into the biology of things? Well, when we look at these major continental plates, we know that at one point in Earth's history, they were all together. They were all big puzzle pieces that fit together into one giant landmass, and that's what we know as Pangaea. So about 250 million years ago, these plate movements brought all of these previously separated landmasses into this supercontinent Pangaea. Life was very much colonizing land and evolving and changing, and so organisms were moving across all of these continents because it was one big mass. Eventually, those plates reversed and things separated back out again, all right, creating those ocean basins, giving us these shallow watery environments, starting to set up different climates, so on and so forth, until we get to the continental distribution we see today. So we can talk about fossils that show up here in the corners of South America, also showing up here in Africa. Why can we find dinosaur fossils on virtually every continent on Earth? Well, because of Pangaea. Interesting thing is that these plates continue to move. They continue to separate across the Atlantic Ocean. It's actually growing a little bit each year. while the Pacific Ocean is shrinking. So eventually, these guys, we believe, will continue to separate until places like California and Alaska run into places like China. Japan gets squashed in the middle, so on and so forth, and we sort of reform another supercontinent.